Hello, I'm Paul Beckwith, and I'm continuing on the thread of my previous video on climate restoration, looking at solutions to the greatest threat that's facing humanity and nature today. It was either pack for my Madrid, Spain trip or film a couple videos, so clearly you see what went out. I'll have to do the packing later. These are a couple of the props that I'll be bringing to the conference, including this is the Norwegian gnome, Santa-like gnome. You know, it's the protector of the garden or protector of the earth, some people say. So during my trip to Kragerø, Norway, in um, in 2015, just after the Paris COP, I picked up this little guy, this gnome from in Norway. Okay, so let's get right back into climate restoration. So I was discussing this white paper from the Healthy Climate Alliance, and I'll just go down to where I left off before. So basically, the whole idea is to restore climate to a safe, healthy climate that we had over a century ago. And that means getting greenhouse gas levels down, CO2 specifically from 415 parts per million down to below 300 parts per million by 2050. So how would we go about doing this? We would need to sequester 1 trillion tons of carbon dioxide. Capturing 1 trillion tons and storing it forever sounds gargantuan. Sounds like a gargantuan task. It is. But while it's not yet widely known, both the technology and financing methods to restore the climate basically already exist. Okay, you know, we need to scale up the technology. We need to scale up the technologies, and we would need to figure out ways to finance them. To make, you know, this is without government financing. If the government steps in, it could be done all that much quicker or more likely occurring. So basically, the proof that we can restore the climate is written in stone, according to the Healthy Climate Alliance. And again, I'm conveying to you all of the things that they claim and the information that they talk about in a white paper. I don't agree with all of this. I agree with, you know, well over 90%, I would say, of what's in this document, but that doesn't mean that I agree with everything in here, but I'm conveying it to you. So in 2017, a Swiss startup company launched the world's first commercial plant to pull CO2 out of the air. The company Climeworks developed a scalable, low-energy CO2 filtering machines that can operate anywhere. In Iceland, there was a CarbFix project that captured CO2 from a geothermal plant and pumped it deep into porous basalt deep under the ground. The CO2 binds with minerals in the basalt, like calcium, and becomes carbonate rock like limestone in a few months. They thought it would take years and years to decades to become rock, but it took a few months. Combining these two projects together, you can actually capture the CO2 from the air and fix it into limestone. If enough carbon removal machines could be built to sequester all trillion tons of excess CO2 by 2050, you know, then we would basically be able to bring down the levels in the atmosphere down to that 300 parts per million. But we need the world to mobilize to do this. No major breakthroughs are needed, according to this white paper. The methods are decades old. Climeworks and CarbFix 2 refined the process with smart engineering and financing to commercialize it. Now, they're not alone. Companies have been developing carbon removal and storage for mineralization in Oman, Australia, Canada, the US, South Africa, and parts of Europe. The current cost is $600 to store a ton of CO2. Climeworks expects that to drop to $100 a ton by 2025. At $100 a ton, deep underground sequestration of all excess CO2 by 2050 would cost about 100 trillion or 3 trillion a year for 30 plus years. The global economy is 80 trillion a year. Global military spending is about almost 2 trillion a year, just to give you an idea. So it's tough to do, but the numbers are within the realm of possibility. Why isn't the world clamoring for carbon removal and storage? And this is a bit baffling. The technology, some people say the technology doesn't work and you couldn't scale it up. According to Healthy Climate Alliance, you can. Is a healthy climate worth government funding? So climate restorationists suggest that the climate community and policymakers are not rushing to do this because the world has not yet set the explicit goal of climate restoration yet. Governments aren't budgeting for it. People don't talk about it. Climate advocacy groups are not asking for it. Okay, so, it's more of an educating the public on what we can do, these ideas, and what is possible. Climate restoration is emerging as an idea whose time has come. The first annual Global Climate Restoration Forum, led into the 74th UN General Assembly, signals a turning point for global leaders to commit to restoring a climate favorable to humanity's survival and forge a coalition to make that happen. Okay, so defining a climate restoration solution. Okay, it has to be, okay, so one of the things is that sufficient basalt. Basalt's a rock that makes up the ocean floor, basically. It exists on every continent, too. If the world mobilized to restore the climate, we could build enough carbon removal machines to lock away all the excess CO2 by 2050. Okay, so the criteria for existing climate restoration solutions, it's got to be permanent, sequester carbon permanently. That's at least for 100 years. It's got to be scalable to get up to 50 gigatons of CO2 sequestration a year, and it's got to be able to be financeable. Okay, permanent, be out of circulation, CO2 out of circulation for a century. Mineralization is permanent, so mineralizing CO2, capturing it into rock. Fizzy drinks with captured CO2 isn't permanent. Carbon neutral fuels, enhanced oil recovery, these things aren't permanent. Scalable means we have to scale it up within a decade to remove and store at least 25 gigatons of carbon dioxide per year. With this requirement, two solutions would get you the 50 gigatons, which would be what is required each year. Mineralization and ocean restoration are scalable, so rock and oceans. Financeable means the funding is already available or can be mobilized. Okay, so for example, construction materials. If we made rock as construction materials, the limestone for construction, or seafood from the ocean sequestration and fertilization, those things could be financeable because they're both going to, generate huge amounts of revenue to continue the process, even without a price on carbon. So methods not financeable are those like reforestation, direct air capture. Those have to be funded by governments and by offset credits. Remember that the global economy is about 80 trillion per year, global military spending close to 2 trillion a year. It would take about 3 to 5% of global world product per year for 20 to 30 years to fund this climate restoration. Okay, so without government funding or public funding, you need to have commercial markets. And the two markets that exist right now, rocks and fisheries. Okay. It talks about a lot of other different things, precautionary principle, etc. But I'll get to some of the nuts and bolts here. Okay, so here's, how CO2 removal and storage methods compare on the 3 climate restoration criteria. Okay, so here's synthetic limestone. The company Blue Planet in 2019 says, yes, it can be scalable to greater than 25 gigatons per year. Yes, can be paid for by the construction industry buying the limestone and the Portland cement and aggregate that they buy anyway. Yes, the CO2 is sequestered for over 100 years, so it's got the permanence. The limestone that you produce is well suited to construction. You don't need to quarry the limestone anymore. You actually produce it. You pull CO2 out of the atmosphere and you produce the rock that you then use to build roads and highways and bridges and buildings, etc. Okay, the ocean iron fertilization method, OIF, is scalable also, can be paid for by sales of commercial fishing licenses and taxes, because fish, you rejuvenate the plankton, base of the food chain, you get You get a cascading all the way up the food chain. You get a plethora of life in the oceans, in the dead zones of the oceans, and the ocean deserts essentially, and you sequester huge amounts of CO2, and it provides food and livelihoods for struggling coastal communities. Along with the ocean iron fertilization, you do marine permaculture arrays. So you basically put, marine permaculture is putting floatable arrays into the ocean so kelp can grow on them, and oysters and all of the bottom-dwelling substances at different depths. These things can be floating in the gyres of the ocean where you get the ocean iron fertilization, so it stays within the gyres longer than it would in other places, and you can sequester huge amounts of CO2. Direct air capture, you could scale it, but you would need government or donor funding. Ocean alkalinization is to get rid of the sequester CO2, remove CO2 from the oceans to address the ocean acidification problem, to reduce ocean acidification. Bioenergy with carbon capture and storage, I don't like that technology too much. It's mostly talking about using, capturing, growing plants and trees on land and incinerating, cutting them down, incinerating them, capturing the CO2. I mean, it competes with the food supply on land. I don't think it's scalable. Agriculture, forestry, and improved land use, improve soil health, but these things, how do you finance them? Are they scalable? Ocean downwelling is putting the CO2 down below, under 500 meters, where it then will sink to the abyss. So, those are all of the different methods. So getting back to the limestone, making the synthetic rock for construction and paving, carbon dioxide can be mineralized above ground as well as in deep basalt. So these companies are developing ways to use captured CO2 in the production of concrete and other building materials. So not just the concrete, which is the glue or aggregate, cement, which holds the concrete together, but concrete is basically sand and gravel aggregate, 60 to 75% sand and gravel, 10 to 15% cement, which binds the aggregate together, and water, 15 to 20%. Synthetic limestone can replace the quarried rock, and you can make the limestone by capturing the carbon. And there's a company called Blue Planet that is doing this. And, you're basically mimicking how shellfish make seashells from calcium and CO2 dissolved in seawater. And in 2016, workers poured carbon-negative concrete for a boarding area at San Francisco International Airport, demonstrating its viability for paving and building. By 2030, substituting synthetic limestone for quarried aggregate rock could pull 50 gigatons of CO2 per year from the atmosphere. Okay, and the construction industry would pay for these materials, and every time you built roads, concrete bridges, buildings, etc., you'd be storing that captured carbon. Okay, restoring the oceans, ocean iron fertilization, photosynthesis in the ocean is the fastest biological way to remove CO2. On land, most plants sequester carbon for a few decades or less before they burn and rot, and that returns the CO2 to the atmosphere. Okay, the forest litter, etc., is decomposed by microbes, and CO2 goes back up into the atmosphere. But in the ocean, most of the plants sink. They carry CO2 to the depths. Once below 500 meters, they can remain there for 1,000 years. And the oceans, of course, cover 71% of the planet. Ocean photosynthesis is doesn't have to compete with food production, produces food. Underwater forests never burn. The growth rate for underwater forests is huge. Kelp can grow up to 2 feet per day. Okay, and then there's a whole ecosystem within the kelp beds. Now, so this is a very key method, and it would just be a small fraction of the oceans, 1 to 2%, that would be involved. Fisheries in the world are in trouble, so the marine permaculture in combination with ocean iron fertilization could actually capture huge amounts of carbon and provide food for our growing populations. Okay, so these marine permaculture arrays could become a key thing. Ocean iron fertilization, okay, the missing ingredient for plants in the ocean is iron. So iron fertilization is a key way to capture huge amounts of CO2. Thanks for listening.